To start this lesson, let's consider Z8 containing the numbers 0 through 7, and we already know that Z8 is a group under addition modulo 8. And then let's consider a subset that we'll call H, a subset of Z8, containing the evens, so 0, 2, 4, 6. And so as our first task, if you could pause the video and verify that H is also a group using the same operations as Z8. In other words, addition modulo 8. And when you do that verification, you may assume that addition mod 8 is associative. So not necessarily worry about that particular group property. All right, well, let's go through the verification. And since H only has 4 elements, it's fairly small. I just constructed a group table right there. So 4 by 4, 16 numbers in all. And I'll also emphasize that the operation here, it's the same operation as Z8. So that's important, which means we are doing not only addition, but this is done addition mod 8. And so there's the group table there. And let's just go through the group properties. So is H closed? Well, we can see that right away because all the sums that we get are either 0, 2, 4, and 6. So what happens in H stays in H. So that's a check. You can put a check mark next to that. And let's just reveal the other ones. We're going to assume that addition is associative, so let's skip that. 0 contains the additive identity element. That's right there, the 0 elements. And we see that the first row in the first column signifies the additive identity. So H contains the 0 element. And then every element of H has an additive inverse that's also in H. So it's very self-contained. So 0 is a self-inverse right here. I'll mark the identity elements. 4 is also a self-inverse. And then 2 and 6 form an inverse pair. And again, everything is self-contained. If an element A is in H, then its additive inverse is also in H. And therefore, H is not only a subset of Z8, but it's also a group on its own, using the same operation as Z8. What we just saw is that our subset H is not just a subset of Z8, but a subgroup of Z8, because it happens to be a group on its own using the same operation as Z8, namely addition mod 8. And so here's a generalization. Let G be a group, for instance, Z8. Then a subset H of G is called a subgroup of G if H also happens to be a group using the same operation of G. And so that part about using the same operation of G is important. To illustrate that, here is a non-example. Now we've seen U8 containing 1, 3, 5, 7. U8 is a subset of Z8. And U8 happens to be a group as well, except U8 is a group under multiplication, whereas Z8 is a group under addition. And so the operations don't match, and therefore U8 is not a subgroup of Z8, even though it's a subset, because the operations, their group operations, are different. And so here's kind of a quick visual. We have Z8. This is all of Z8. But Z8 is an additive group under addition. And so we see 2 subsets of Z8, actually splitting the whole group in half. This subset H is a subgroup of Z8 because it's a group under the same operation, namely addition. However, this subset U8, again, even though it is a group, it's not a subgroup of Z8 because the operation of U8 is multiplication, which is different from the operation of Z8. And so that's just something to be careful about when we discuss subsets. And now please pause the video and work on day 11 classwork. And afterwards, we will go over some of the problems and concepts. Here's a scenario that we'll encounter often in this class. Suppose we're given a group G, and so something that we already know is a group. And then we're also given a subset of that group, and let's call that H. So in the classwork, for instance, we were given the group G of Z10. Those are 2 by 2 matrices, entries in Z10 that have multiplicative inverses. And we've already seen that such a set is a group under matrix multiplication. And then we considered its subset H that we call S of Z10. Those are matrices that have determinant 1. And our goal is to show that H is not just a subset of G, but a subgroup of G. And so that's our aim. So let's first talk about the steps involved. And here's kind of a visual that we'll keep. Again, we already know that G is a group, and we have this subset inside it called H, and we want to show that H is not just a subset, but a subgroup. And that really boils down to showing that H is a self-contained group on its own, using the same operation as G. And so here are the things that we need to show. First, we need to show that H is closed under the same operation of G. And so if A and B are elements of H, so let's say here is an element A, and let's say here's an element B right here. Now, we want this product A times B. We know it's going to be somewhere inside G because we already know G is a group and hence closed, but we don't want A times B to be somewhere outside of H. We want A times B to be inside H. So let's say right there. So that's one thing we need to show. What else do we need to show? Well, associativity. However, keep in mind, we already know G is a group, and that means the operation of G is already known to be associative. And H inherits that same operation from G. And therefore, we already know that the associativity holds for H, the operation for H, because again, we're using the same operation that G uses. And so there's really nothing to check there. And so in a typical subgroup proof, we don't even mention associativity because that's just a given by the fact that G is already a group. So that, I'll just put a check next to it. No need to even bother. Now let's talk identity. Again, because G is a group, we know G has the identity element. What we need to show is that not only the identity element in G, we need to show that the identity element is inside H. And so we don't want the identity element, say, somewhere out here. And then last but not least, inverses. So if little h is an element of H, so let's say H is right here. Now, we know H inverse exists because, after all, this little h is sitting inside G, and G is a group. We just don't want H inverse to be somewhere out here. Instead, we wanted it to be contained inside H. And so as you can see, all the elements that we're interested in, we wanted it to live inside H because we want H to be a self-contained group on its own. So those are the things we need to show. And let's apply these ideas to the example that we have of our matrix groups. So here's the theorem that we like to prove. Consider the group under multiplication, G of Z10. and its subset S of Z10 consisting of those matrices with determinant 1. And our goal is to show that S of Z10 is not just a subset of G of Z10, but a subgroup of G of Z10. And so let's do a rough draft of it. As we just discussed in the previous slide, we need to show closure identity inverses. We don't have to worry about associativity because, once again, S of Z10 inherits the multiplication operation from G of Z10, and we already know G of Z10 is a group. And so for closure, if alpha and beta are in S, we need to show that their product is in S. Well, if alpha and beta are in S, so that's kind of our starting point, what do we know? Well, to be in S means that their determinants are both 1. So we know that the determinant of alpha is 1, and also the determinant of beta is 1. Our goal is to show that alpha times beta is in S, so we need to show that alpha times beta has determinant 1 as well. Well, we can use the fact that they each have determinant 1, and we can compute that determinant of alpha times beta we know is equal to determinant of alpha times determinant of beta, and that's 1 times 1, and therefore that's equal to 1, and thus we conclude that alpha times beta is in S because we just showed that its determinant is 1. Now let's talk identity. Again, we need to show that our identity element, epsilon matrix, is in S. So we just, for that, we just compute its determinant. And so let's just do the calculation. What's the determinant of the epsilon matrix? So it's 1 times 1. Main diagonal minus 0 times 0. And that's equal to 1. And we just showed that epsilon is in S. So finally, we have to show that if alpha is in S, then its inverse, which we already know exists because G is a group once again. We just have to show that alpha inverse not only exists, but exists in S. And so we have to show that alpha inverse has determinant 1. Well, from this part, we already know that the determinant of alpha is equal to 1. So that we already know. And so let's write it this way. And then what about alpha inverse? Well, we have to show that that matrix is in S. So we need to compute its determinant. But here is where we can use the property of determinants. The determinant of an inverse matrix is the inverse of the determinant. But we already know that the determinant of alpha is 1, and the multiplicative inverse of 1 is 1. And therefore, alpha inverse is in S because its determinant is also 1. And so that's the rough draft. And then based on this, let's write down a complete proof in the next slide. So let's write down a complete proof. I think of a subgroup proof as really 3 mini proofs in one. It's the closure, identity, and inverses. Again, we don't even mention associativity because that's a given from the fact that G of Z10 is a group. And so let's start with closure. This is really just following what we did in the outline. So we'll let alpha and beta be elements of S, and by S I mean S of Z10. And therefore we can say that their determinants are both equal to 1. Determinant of alpha is 1, and determinant of beta is 1. Now we need to show that alpha times beta is an S, so we just show that its determinant is also 1. So thus, determinant of the product alpha beta is equal to determinant of alpha times determinant of beta, which is 1 times 1, and that's equal to 1. And so we just showed that the determinant of alpha beta is equal to 1, and hence we can say that alpha times beta is in S, so that S is closed under multiplication. S is closed under matrix multiplication. And so there is closure. Now let's do mini proof number 2, namely the identity element is in S. And so we can just do it right under here. We ultimately want epsilon to be in S, remember that, and that means we need to show that its determinant is equal to 1. Well, so let's write down what epsilon is here, 1, 0, 0, 1, and that's 1 times 1 minus 0 times 0 is equal to 1. And we just showed that the determinant of epsilon is equal to 1. And so we can say, thus, the identity element is in S. So that takes care of the identity. And last but not least, the inverses. So we've already defined an arbitrary element alpha there, so we can work with that and show that its inverse is in S. Or if you like, you can introduce a brand new element like gamma and show that gamma inverse is in S, assuming that gamma is in S. But I'll work with alpha there since that's what we did in our rough draft. And so we can say, for instance, recall that alpha is an element of S as already defined. Then we have, again, we want to show that alpha inverse is in S, so let's compute its inverse. And so that's the inverse of the determinant, which is 1 inverse, which is equal to 1. And so we just showed that the determinant of alpha inverse is equal to 1, and thus we can say that alpha inverse is also in S. And that's the proof. And so I'll just write down the final line. In other words, therefore, S is a subgroup of G of Z10 because we showed that it satisfies closure, identity, and inverses. Associativity again comes for free, so we don't even have to mention it. To wrap up this lesson, let's talk about the first question in the classwork. What are all the subgroups of Z8? Well, we already know we started this lesson with 0, 2, 4, 6. That's one of the subgroups of Z8. That has 4 elements. We also saw that the set with just the additive identity element, that's a subgroup of Z8. That has just 1 element. Here's another subgroup of Z8 containing 0 and 4 only. And that has 2 elements. And then Z8 itself is a subgroup of Z8, and that contains 8 elements. And so there's something about the number of elements in each of these subgroups that we'll talk about in a later lesson. So for now, just something to think about, see if we can recognize some patterns, make some conjectures. But for now, this is the end of today's lesson, and I will see you next time.